This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
That it has no side effects and the order in which you evaluate it doesn't matter, so that we can change it around, right? And we'll see the same kind of effect in Prolog too, right? When we write a pure Prolog program, then we can change things around without changing the set of answers. And that means that we can change how long it takes to compute, right? Just like in Haskell.
So if I try to make my code run faster, I should use folder instead of using the built-in functions.
So I don't see what you mean by the built-in functions.
Like length.
No, but length will be converted to folder. That will be its library definition.
So
Okay? Yeah. So basically that definition of length will be what's running, okay? Because exactly what I was talking about, that when they see folders or maps or whatever, then they'll say, oh, there's an opportunity to do some things. Things like, they're called deforestation is one of the things they try and do, right? Which is basically instead of doing something to a list to build another list and then taking that list and building another list, just try and do the whole thing in one go and build the final list right from the beginning, okay? Yeah, so you don't, they've already thought about the best way of implementing all of their built-ins. So anything used in the library will be good. Whether it's implemented using another library function or not doesn't really worry you. Yeah. Okay, so we looked in the last lecture, it seems like an infinitely long time ago, at Datalog. So Datalog is a simple version of Prolog, a subset of Prolog, which basically allows us to do any kind of database operations we want, right? But we want to be able to do more than that. We want to have a full programming language. We actually have to be able to create new values. So we need to have more than just a set of constant values to play with. So in Prolog, all of our data structures, so there's no types in Prolog. Everything is just called a term, all right? So a term can be an atomic term or a compound term, or it can be a variable. And basically in Datalog we only had atomic terms, right, which is just a single constant like Queen Elizabeth, or we had variables, nothing else. So we can also have other kinds of atomic terms. We can have integers or floating point numbers, right? So I've just written down, they're just another atomic term. And then, so an atom, these sort of constants we saw before, the rules for that are they start with a lowercase letter, yeah, and they're followed with letters, digits, and underscores. So Queen Elizabeth, we've already saw, banana, these kind of things. And as I pointed out last time, it's kind of the opposite of Haskell. In Haskell, when we write a data constructor, or a type name, but if we write a data constructor, it always starts with an uppercase letter, right? In Prolog, when we write a data, it starts with a lowercase letter, and when we write a variable, it starts with an uppercase letter. Okay, you can write complicated atoms by putting inside single quotes. So I could write single quote Queen Elizabeth or Hello World, something like this, and then I can use any kind of, I can use these escape characters, the usual things that I used to from C. /n for new line, /t for tab, and /quote for a single quote, because if I want to put a single quote, then I can't do it, because it would be closing the quotes. All right, so that's atoms. And then the syntax of Prolog is made up of compound terms. So we have atoms and we have compound terms. And the compound term is functor, right, or function symbol, which is basically exactly the same as an atom, followed by 0 or more arguments. And as soon as you have more than one argument, you put them in parentheses and separate them with commas. Right. So our functors are exactly the equivalent of Haskell's data constructors, except they're not typed. So remember, we've seen some small trees in Haskell. I would write something like this. Node, all right, so this is a tree which has a left child, which is just a left child, which is just a single leaf. It contains the value 1, and it has a right child, which is this tree, which is a node containing just the value 2 and 2 leaves. Yep, that's how we'd write it in Haskell. How do we write it in Prolog? Well, here's the outer loaf node, right? Here's its left child, it's a leaf. Here's the value, it's a 1. And here's the right subtree, which is this, which again is a node with a leaf and a 2 and a leaf. Okay, so just different syntaxes. Right, so this is much more, I guess, much more familiar to things. These are kind of how I'd think about things writing functions in many other languages, right? So this is just a term, exactly the same as Haskell things, just an object, just some, basically a way of storing information. Okay, because it's dynamically typed, there's no types, I can just put any term under any other thing. Yeah, so no need to declare types. And there's some special syntax for functors, particularly infix notation. We'll see some of that later on. Okay, so we've got atoms, we've got compound terms, and we've got variables. And variable is also a term, obviously. And as I said before, a variable name begins with an uppercase letter. Right, so the opposite of Haskell. Followed by any number of letters, digits, and underscores. And we've got a special variable, underscore, exactly the same as in Haskell. That underscore is a special variable, right? It's the unnamed variable. So we use it in Haskell in pattern matching, right? If we want to match something, but we don't care about its name. It's almost exactly the same usage. And the underscore is in prolog first. Again, like Haskell, a variable only ever takes one value. We're not talking about storage locations, right? We're talking about like mathematical variables x. So if I write down x equals x plus 1, there is no solution, right? It's not like in a procedural language where you say x is actually the name of a storage location, and when I write x equals x plus 1, I say take the value that's stored in that location, add 1 to it, and put that result back in that location. It's a very different statement. The mathematical statement x equals x plus 1 says, find me an x which is equal to 1 plus itself. And the answer is none. Okay. And then the arguments of a compound term can be any term, so they can be variables. Right? So I can write f of AA. So what does that denote? It denotes a term, right? An f term, which has two arguments which happen to be the same term. Right? They have to be the same term. I can write f of underscore underscore, and that just says this is f which has two arguments which both could be any term. Okay? Because underscore is a special variable. Yep. So those two underscores are treated differently, just like we do if we have two underscores in a pattern match in Haskell. Okay, and we have special syntax for lists. The empty list is exactly the same as Haskell. And a fixed length list is exactly the same as Haskell, right? We just write the list with the square brackets with the commas in between. The difference is when we look at how to denote unfixed lists. So in Haskell we're used to this, right? This is x cons x's. So that's a list whose head is x and whose tail is x's. And we write that in prolog this way. Right? So x, the vertical bar x's. And don't confuse this with Haskell's list comprehensions. Right, which looks similar to this. And indeed, we can put any number of elements of the list in the first part. So in Haskell, we'd write x1 followed by x2 followed by x's. That's a list which has first x1, then next x2, and then the rest of the list is x's. And we write that this way in Haskell, in prolog. Yeah, so two different syntaxes. All right. Now we're going to be interested in looking at our terms, and we got two classes of terms. So we have ground terms. A ground term is a term which has no variables in it anywhere. So a ground term exactly represents one thing itself, right? Whereas a term with a variable in it, or any number of variables in it, means, well, it could be any number of terms, right? We could give values to those variables and we could get a different term. Right? So 3 and f of a, b are ground terms, but name, just a variable itself, right? That's a placeholder for a value that we don't know yet. And f of ax is non-ground, and this is saying, well, this is going to be a term of the form f of a, and then whatever's value x is going to take gets slotted in here. Yeah? And this is one of the things that we're not used to seeing in other languages. That we can actually build, we'll actually reason with and compute with terms where we don't know all the results yet. Okay. And then that brings us to how we move from non-ground terms to ground terms, and that is this idea of substitution. Okay, so substitution means that we consistently replace some variables by another term. Okay, so it doesn't have to be a ground term. Yep. So they only ever replace variables, never atomic or compound terms. So we think a substitution is a mapping from a variable to a term, which doesn't have to be ground. Here they're all ground. Yeah. So this says replace x1 by leaf, replace x2 by 1, replace x3 by leaf. And so if we apply that substitution to this term, right, you can see that this becomes this, because the first x1 gets replaced by leaf, the x2 here gets replaced by 1, the x3 gets replaced by leaf. And we get that result. Okay, does that make sense? And because we can do this, we also have this notion that this term here is an instance of this term, right? Because there is a substitution which will map this term to another term. The first term is an instance of the second, right? So any ground prolog term only has one instance, right? We can't do anything to a ground term. It's got no variables left in it. But any non-ground term has an infinite number of instances. As soon as I have one variable in there, I can replace that variable with all of the numbers from 1 to as big as you want, for example. Right? Or I can build lists containing the value 0 n times, however many n that I want. Okay. And so some notation that we're going to make use of is this idea. We have a substitution, remember, which is a mapping from variables to terms. And we've got a term t. We want to apply that substitution to the term. We write it as t theta. So we write the substitution after the term. Yep. And so then we can think about the instance of. So we know that u is an instance of a term t if there's some substitution, right, where u is equal to t theta. So this allows us, this is talking about basically ordering of terms. If you think about it, u represents less possibilities than t, right, could ever take. And we also have this notion of unification then. So this is where we're trying to get to, because this unification is going to be the core of what actually happens when prolog executes. Yeah? So you basically need to understand unification. So a substitution is a unifier if you have two terms t and u, and if you apply the substitution, they become the same. Right? They become exactly the same. Nothing different about them. So if we look at this example, f of xb and f of ay, to make those two terms, if we applied the substitution xa, right, this would become f of ab. Right? But they're not identical yet, these two things there. But if we apply the assumption x equals a and y equals b, okay, it's a very simple case, then both of them, this one becomes f of ab, this one becomes f of ab, and they must be the same, so that is a unifier of those two terms. Yeah? And in fact, in this case, that's the only unifier, right? Because in order for these two things to be equal, well, if I think about it, this thing has to be equal to that thing, so x has to be equal to a, and this thing has to be equal to that thing, so y has to be equal to b. So in fact, that's the unique unifier for those two terms. But in general, we may not have a unique unifier. All right. So what I want you to do is now construct some unifiers. So what substitution is it? So what are we going to do for, there's three variables here, x, y, and z. Give me a unifier that makes these two terms the same. So remember, the same just means absolutely syntactically identical. Yeah? That's one thing we'll find out about later in prolog. This thing, 1 plus 3, and this thing are not the same. Remember, write it down, commit to an answer. Commit forces you to at least have a go. All right? So, who got it right? Some people, very few people. Who attempted it? A few more people are willing to hand out their thing. Let's think about what's going on here, right? This branch, this leaf. So these two things, to make them the same, I really have to replace x with a, right? And here, to make these two things the same, I really have to replace y with b. And for this, I don't have to do anything. They're already identical, right? I don't need to change z because whatever value z takes, they'll still be identical. So they're already identical, don't have to do anything to z. Okay? So I could, if I had z goes to c, that would also make them identical, but there's no need. Yeah? So this is the kind of the least amount of work to make them identical. Okay, what about this one? All right, hopefully you can see that there is no substitution that will make them the same. Okay, because if we had to, what would we do? We would look here and we'd say, well, in order for these two things to be the same, because they're in exactly the same position, x has to be a. In order for these two things to be the same, x has to be b. I can't make x both a and b at the same time, right? A and b, remember, are different things. If they look syntactically different, they're different. That's what we think about in Prolog. If a term is different, it's different. There's no way I can unify these two terms. So this one is not an instance of this one. There is no unifier. Yeah. All right. Now, how about that one? Commit. Either write down a unifier or say they're not unifiable. There's no way I can make one into the other. Let's look at the first argument of branch. The first argument of branch is, so they're the same at the top level, right? Then we look at the first argument. This one is branch of leaf of x, leaf of b, and this one is leaf of a. There's nothing I can do to make those two the same, right? This term starts with branch, and this term starts with leaf. It doesn't matter what substitutions I do, they'll never be the same. Yeah? All right. Just to make you think a bit harder, what about that? Those pair of things. What substitution could I do to make those two the same? That's x1 and x. It's only branch, just has 3 arguments. So you've got to remember these are just terms. It's like I have exactly a node with the 3 arguments in the node. Just a way of tripling up things with a name at the front. That's what you think about as functors. The closest thing in Haskell, well, Haskell is a declared data type, right? Where you have the functor at the start and then you have the arguments. That's exactly what branch is, but we don't declare it. The branch with 3 arguments. So you can also use branch with 2 arguments if you want, but branch with 2 arguments, of course, is never going to be the same as branch with 3 arguments because there's no substitutions which add new arguments. Right? All right. Who thinks there is a substitution that'll do this? Yeah? Who thinks? And so no one else is. Who thinks there isn't? A few people say no. All right, so normally in Prolog there isn't, although there are interpretations or versions of this where there is. Okay? Because what happens? In order for this to be true, we have to make x the same as leaf of y. Yep? So they have to be equal. We can make z to 1, that's fine. But now, what do we have here? This has really been replaced by leaf of y. We have to make y equal to leaf of y, right? And basically, if we think about it, it's a bit like my x equals x plus 1 question, right? There are no integers where x equals x plus 1. And if we think about our terms as only finite, there are no terms which solve this constraint, right? There's no term which is both y and leaf of y. But interestingly, if we think about infinite terms, there is one, right? The infinite chain of leaf going off forever actually does satisfy this equation, right? Because if I take an infinite number of leaves and I add one more leaf on the top, I still got the same thing, yeah? But in Prolog, it'll say no. Because in Prolog, we standardly deal with finite terms, right? Although we've got to be careful, Prolog won't always detect it. Okay, so let's start off to write some recursive code. So we know that a proper list in Prolog is either empty or it's a list. This is x, an element, and y must also be a proper list, right? So we write this, we say proper list empty, so we know that the empty list is a proper list. Remember, this is a predicate. This statement is true. And if we have a list of the form head tail, right? So just like in Haskell, when we're writing code that works on lists, we're typically going to have 2 cases. One case for the empty list and one case for the non-empty list. Right? So this is our 2 cases. And for this to be a proper list, then the tail has to be a proper list. Right, if we run this, we load this into our Prolog system, we're going to get back a warning, singleton variable head. Right? But it'll all work. So let's have a look at that warning for a moment. So this is because if we look at this clause, the variable head only occurs once. Yeah? And so that's very unusual. Right? If a variable only occurs once, you're basically not doing anything with it. You're just pattern matching and throwing it away, or you're creating a new variable out of nothing to do something with it. So it very often means that your code is not correct. So if we've misspelled tail as tile, right, then both tail and tile would also occur once. And so because it's very common to do these kind of things where you misspell a variable and only have one once, Prolog will actually warn you if you see only a single variable to say, hey, looks like your code is buggy. Right? So you're going to find out from Prolog you'll get a lot less error messages than from Haskell, right? But Haskell's error messages are painful and incomprehensible, right? And then you come to love them because at least they tell you something's wrong with your code, right? In Prolog, almost all code is valid, right? So this is a warning, so it's still valid code, but it'll give you a warning at least because it represents a very common kind of error. And the way to fix this So you should always try to get rid of warnings, right? You can leave them in there, obviously it's not necessary. If you look at them and you say that warnings are fine, then actually, whatever language you're using, get rid of warnings, because otherwise you can get to the point where you've got hundreds of warnings coming out when you're compiling the code and you're ignoring them all, and the really important warning that's in there you don't see, right? So the rule for Prolog is if you have a variable that's only used once, apologies, when you have a variable which only used once, you start it with an underscore in its name, and that just tells the compiler, don't give me a warning about this because I explicitly expect it to only have one usage, right? It's just another name for a variable, but this one it'll never warn you about. So the other thing is you could just put an underscore there, right? The anonymous variable, because you don't do anything with this variable, so it doesn't need a name. Yeah. And as I said before, always fix compiler warnings, regardless of what language you're working with. Right? It's worth the effort to get rid of them so that anytime something happens, a new warning comes up, you notice it and you can think whether it's a problem that you should be dealing about or not. All right. So let's look at basically the first version, first code, Prolog, non-datalog code that anyone starts with. And here is the append code. Right? So remember, we're basically doing the same as the plus operation for Haskell. So we have to think of two cases, right? We're appending the first list to the second list to give the third list. So remember, in Prolog, we just have arguments. We don't really have inputs and outputs anymore. Of course, we typically write our program so that the early arguments are the input and the later arguments are the output. Yeah? So if I want to append an empty list onto the front of C, it's easy. I just get C, right? That's the easy case. If I want to append a non-empty list onto C, then what should I do? I should take the rest of this list, append C onto that, that'll give me BC, and then I put A on the front of that. Right? So I'm saying, you've got to think about it logically speaking. If it is the case that appending B to C gives me BC, then it is the case that appending A followed by the list B to C gives me this list. Right? That's what we're actually writing. We're actually writing a piece of logic which says there's this relationship between the append relation. Right? So don't think of it as coding. Right? It says that's how we understand it. It is a fact that appending the empty list to C always gives you C. Right? And it is the case that if you append B to C to give the list BC, then you can append the list AB to C to give the list A BC. Yeah? And of course we can ask questions like this. Okay, if I append ABC to DE, then what's the list? And there's the answer. Yeah? And again, we're going to think about this like translation. How this works, we'll look in a moment. Okay, so again, as I said before, this kind of, we'll see this common pattern. If I'm doing some sort of coding on lists, then I'm going to have one case for the empty list and one case for non-empty list, and that's exactly what I'm doing here, right? I'm pattern matching the empty list and the non-empty list here. The second argument I do treat differently, and then I go on. Right, so even though this proper list is not very useful, yeah, it's not code that you're going to use very much because all it does is check if something is a list. It's actually, we can use it for exactly that definition to make sure, because append is only really meant to work on lists, right? But that code will work on anything. In fact, will even succeed for non-lists. Okay, so append, because we're talking about a relation, right? I told you there aren't any notions of input and output. Okay, or we like to think in Prolog there's no idea of inputs and outputs. We're just talking about relations between the arguments. So I can use the same code to do all kinds of things. So I can ask this question. If I append 1, 2, 3 to a list rest and get the list 1, 2, 3, 4, 5, what was rest? Yeah? So I can extract part of it out. Or I can say, if I append some list called front onto 3, 4 and I got the list 1, 2, 3, 4, what would front be? Okay, and here again we can see this difference. Here, Prolog knows there's one answer and one answer only. Yeah? Because it can use the information here to pick which of these two clauses it needs every time. Here, we're giving it an unknown list at the front. So it finds one solution, 1, 2, but it then doesn't know if there might be more. In this case, we search for more, it says no more. Yeah? We can even ask this question. Give me two lists whose appending is A, B, and C. So if you append them together, you get A, B, and C. And we're going to get answers, okay, if the first list is empty and the second list is A, B, C, that would work. If the first list was A and the second list was B, C, that would also work. If the first list was A, B and the second list was C, that would also work. If the first list was A, B, C and the second list was empty, that would also work, and nothing more. Yeah? So this is the important difference of logic programming over functional programming. So functional programming, we're always talking about functions. We're going to give them their arguments and then we're going to find out the result. Yeah? In logic programming, we're just talking about relationships between arguments. And it's not necessarily that we use inputs and outputs in any particular way. Now, most of the time when we're writing Prolog code, we'll have very strong ideas about how we're going to use the predicate. These will be the inputs, this will be the output. And we're going to take that into account to make sure that our code runs efficiently. But logically speaking, if we're using pure Prolog, then our code should be able to run in any possible direction. Okay, so length is a built-in predicate which does similar things. So I can say length of ABC and it will print the length as 3. Right? So that's how we expect to use length in Haskell. We can also say list, give me a list which has length 3. And I'll get back this. Right? So this is basically a list and it's got something there, it's just a variable, right? Something else there and something else there. You can see from the numbers, basically these numbers are just the order in which the variables are created by the system. So these just 3 different values. So basically this is a representation in Prolog of a list of length 3 with anything in each of the positions, right? Because we can do a substitution to make these values take any possible value. Right? And that's exactly the answer, right? The most gentle answer I can ask. If you want to say, give me a list that's length 3, then this is a generic representation of all lists of length 3. Yeah? So any list of length 3 will be an instance of this. Okay. So let's put them together. So what we're trying to do now, okay, so declarative programming is about learning to think about your code as a declaration of what you want and not how it's built, right? And that'll be even more interesting in logic programming. We're not talking about even a function. We're just talking about relationships between arguments. So we know the take function from Haskell, right? So it takes 2 arguments, takes a number and a list, and it gives you the first n elements of the list, right? It builds a new list with just the first n elements. So how do we build that in Prolog? Well, we can think about the facts. What's the relationship between these 3 things? Well, it's definitely the case that this list, the front of the list, is length n. Yeah? So definitely the case that the answer that I want back is length n, because that's what I'm asking for, the length n part of it. And it should also be the case that it's the front of the list. What's the front of a list? It's something where if I append something to it, I get the list. Right? That's the append. Right? If I append something to front and I get the list, then this list is the front of the list. So if those 2 things hold, then our front is the result of taking the first n things off list. Yeah? So you're thinking about what is the properties of front with respect to list and n that need to hold. That's all I need to do, right? So if we write this, does it in fact work? Right? Yes, it will. Right? Because think about what will happen. Let's say I do take 3 from the list A, B, C, D. We know that length will return a list of length 3 with any variables in it. And then we'll do append, right? I can do it. Steps, I guess. So if I think about what I haven't got the list here, take 3, A, B, C, D, E, F, front. Right? So this is not going to work, but don't worry, that's what it will first make a list of length 3. So we'll go length 3 front. Oh, because I've done the length in the wrong way. Length front 3. Yes. Oops. And there I get back an arbitrary length 3. And then it'll say, well, I need to append that list. Let's just grab that list. To something to get the list. Right? And I'll get, okay, then this thing has to be A, this thing has to be B, and this thing has to be C. There's no other options. So if I put that all together, that's basically saying front equals A, B, C. Yeah? Okay. So we've just seen front. What I want you to do is do drop. We've just done take. Right? So I just remind you what take was. Take n list front was, I had the length of the front list was n, and I had to append front onto something to get the list. Okay, what I want you to do is do drop. Okay, so remember what drop does. It says I take a drop off the first n elements of the list, and then what remains is the backup list. So write me prologue that defines that by just thinking about the relationships between those things. Make a commitment. Even if you're never going to put your hand up, regardless of what question I ask. The point of these in-lecture quizzes is to make you try and use the information I've just put in front of you. That forces it to be stored in your brain differently, giving you much better recall later on in the course. Give you better learning. So you should see that, it's not that different from take. If you'd like more time, no one will put up their hand, so I can get whatever answer I want, of course. Okay. Who'd like to see the answer? No one wants to see the answer, so we can just stay here. All right. basically it's almost exactly the same code, right? We need a front list of length n. We have to append the front list to the back list to get list, but now it's the back that we return. This front we're just using to remove the first n elements. That's not what we want here, right? So we're just almost exactly the same code, except that we're returning a different thing. Here it was this thing that I didn't give a name to, but that was exactly what I needed, right? So I'm just saying create a list of length n, right? Append that to the back list to get list. That means that back must be the part of the list which isn't the front. Yeah?
You also do it by declaring like the variable length list, and then saying back as length the length of list minus n.
Okay, so you could try, yes, you could try that as well. You could say length of list is n, where we haven't done arithmetic, and we could say, okay, then create the let's say L is n minus m or whatever, right? And then I can say back is length of that, and then I can say append front back list. That would work. Yep. So that is a viable solution. People didn't understand it. I'll try it again. Right, I'm going to say length of front is n. I'm going to say, okay, the length of list is m, let's call it. I'm going to say, let's call it L is m minus n. And I'm going to say the length of back is L. Actually, I don't need this one in this case. And then I can go append front back list. Yeah. Oh, dash for front. Yes, I don't need it. I don't need front anymore. But actually this one, because of the way append works, remember how append works? It looks at the first argument and it splits on two cases, right? Empty and non-empty. This is a better way because the first thing this does is makes the list fixed length. So then I always know when I look at that list, is it non-empty or is it empty, right? So this version of the code will be more efficient than this one because append likes to know the length of the first list. If it knows the length of the first list, it knows exactly what to do. Yeah? Whereas here, in this version, it doesn't know anything about the first list, so it's going to have to try both cases. Right, they'll all work, they'll all give you the right answers, but this is talking about which one will I have to search more to find the solutions, and which one will I have to search less. Yes, exactly. So this will basically enumerate cases for this list and eventually find, I mean, because it'll try an empty list first. Yeah. And if that doesn't work, it'll try another one. Basically, it'll only work when the list it tries here is one of length n. So in fact, leaving that in there and putting that front in there would also make it as fast. But then again, then this whole length computation for back doesn't really help you. Yeah. So, in all of declarative programming, right, there's lots of ways of writing down something which means the same thing, which will compute the same answers, right? And eventually, when we get good at understanding these things, we'll work out which ones are the ones that are going to compute faster than the others. And in fact, in Prolog, it's a lot easier. Okay, we'll show you in a moment, or eventually, how Prolog actually executes. Right now, it's still a black box, and we saw how Haskell executes, but that's always a bit of a black box, right? Because Haskell just picks a term to do a replacement on, yeah? And we don't really know in which order it does that replacement. But Prolog actually, it picks a goal to expand, but we know the order in which that happens. And we know the order in which it tries its different alternatives. So we can actually reason much more easily about what's happening when we're running some Prolog code. And when you get good at Prolog programming, you're able to make use of that. Okay. Let's think about another example. Here's list membership, right? So what we want to say, this element is an element in this list. Now, one way to do it is this. Well, if I take the element, a list which contains the element as its first thing and something else, and some other list, and I append them together, then I get list. right? So it means, think about it this way. I can take list, I can split it into a first part and a second part, and the second part starts with element. Right? Now that must be the case if element is in that list. Right? If element is in that list, I can always split the list just before that element, and then this will hold. Right? I'll have the list before the element, the list after the element, and that split will hold. Okay? Right, so that will work, and it will actually be, it will behave the same. It'll give you the right answers. Just thinking logically about if I know how to do append, then I know how to do elements. But I can do it more directly, and this code will be more efficient, by thinking about two cases, right? There's two cases. Well, first of all, there's a missing case here, right? What if the list is empty? Yeah? Then element is never an element of an empty list, right? The empty list's got nothing in it. So there's no way this can be true if the list is empty. So we've left off. We don't have a rule for when the list is empty, right? Because in Prolog, we're only putting in the rules for things which are true, because there's an infinite number of things which are false. We don't want to have to write down all the things which are false, right? In Haskell, remember, we'd be giving this a fixed type, and we'd only have a finite number of possibilities. But in Prolog, I'm giving it any kind of object, so there's an infinite number of possibilities. So we've got the only way it can ever be an element is if it's a non-empty list. So if the first element is element, obviously it's there, right? If we looked at the list and the first element was the element we're looking for, then obviously it's a member. Yeah? What's the other option? The other option is, well, this is not the same, or it is the same, it doesn't really matter. But it's the case that the element is an element of the rest of the list, right? We have this recursive reasoning, just like we've done recursion for Haskell. Recursion will be our only mechanism for doing any complicated computation, right? So it's definitely the case, think about it this way logically, if element is an element of this list, then it's also an element of this list where I put something on the front, right? That's just true. And another thing which is true, that element is definitely an element of a list which starts with it. Right? These are just two statements about membership. They cover all the ways you can be a member of a list. Yeah? Okay, and as I said earlier, 6 by 7 is just a data structure. Everything in Prolog is just a term. So if I write 6 by 7, I'm just meaning that's actually just times with two arguments, 6, 7. Right? It's the same as writing that, but we write it infix just because we want to write arithmetic things infix. So it's a special operator. Just the same as it is in Haskell, right? If we write times, 6 times 7, what we're saying is apply the function time to these two numbers, 6 and 7. Yeah? But in Prolog, it's different. It's more like times is just some data, right? It's just a times term which has two arguments, 6 and 7, right? So if I ask x equals 6 times 7, I get, yep, x equals 6 times 7. Just exactly that same term, yeah? Well, I want to do some arithmetic on it, so I've got is, right? So this says evaluate this term as if it was an arithmetic expression. So in this case, now I get x is 42. So now I've actually done some arithmetic computation. Okay? But you can see that this is going to be tricky because now this is sort of can really only make sense if this is a ground term which only talks about arithmetic, right? Doesn't make much sense if this is a times 7, right? So we can use that, right? We could write a square relation which says, okay, n2 is n squared, and I can just write it that way. And this will work if we give it the first argument, right? We say, okay, square of 5 is x, we'll get x is 25. That's all good. But then we say square of x is 25, right? What's the x which when squared gives me 25? And I'll get this argument, this error. Right? Arguments are not sufficiently instantiated, basically because is not going to work unless this is a ground term. And in this case, you can see what happens is I pass in this is 25, and this is still a variable. So it's exactly the same as I asked this question, 25 is x times x, and I get the same error, right? So basically, this call gets converted into this call, which says that. Right, so later on we'll look at how to do arithmetic that works in both ways, and in fact that's sort of where my research career started, when we're building these languages which allowed us to do arithmetic in all ways, called constraint logic programming, which is now a kind of key technology used for discrete optimization problems. Okay, so we have usual kinds of arithmetic operators. But remember, by themselves, they're just functors, right? They're just constructors. So if I write a minus b, then it just means a minus b. It's only when I use the is function that I can actually work out what that means. We've got arithmetic predicates, right? And they require that both things have to be ground for the test. And notice this, very important, okay? You write less than or equal to this way, equals less than. It's the opposite to almost all other languages. And the reason for that historically is that Prolog is a logic language, and so these things, right, which represent arrows, have been used for their logical meaning. All right, so this is implication, reverse implication. This is implication, but as a predicate. So this was already used. It's actually used in their grammar syntax. And so, different from every other language, we have less than or equal to written as equals less than, because the arrows, at least for logic, were more important than arithmetic. Okay, and we've got equals and not equals when we only apply to numbers. Right? We can always do equals, but that's a different thing. That just checks two things are the same. Equals and not equals will actually evaluate both sides, treating them as arithmetic, and then check if they're the same. Yeah. Okay. So one of the big things, which hopefully you'll like once you get used to it, is that whereas in Haskell you basically ask the compiler to do something and it's a black box, and away it goes and does something, and it takes however long it takes, and you don't really know what's happening. Right? You do know what's happening, and so it's just doing replacement, 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 replacement until it can't replace anymore. You don't really know the order of what's happening, and you can't sort of stop it in the middle and see what's going on. But in Prolog, you can do this really easily. It's one of the reasons that it's a really great language for building rapid systems, because you can easily debug your code without thinking too hard by just seeing what's happening. Right? And part of this is the reason that, unlike in, say, a language like C or JavaScript or anything like that, where an object that you're computing with is this huge monster, you can't even really look at it. Yeah? In Prolog, everything's just a term, and we can print out terms anytime. So we can see exactly what's going on. Right? Okay. So let's try building reverse. Yeah? So this is almost exactly how I'd build reverse if I looked at my reverse definition in Haskell. Right? So how do I reverse an empty list? Well, it's just the empty list. That's easy. Yep. So obviously, yeah, two cases. What if I got a non-empty list? A followed by BC. Well, I reverse the tail, right? From BC, I get CB. And then I take the tail and I add A on that, the end, and that gives me CBA. Yeah, so it's very straightforward, recursive definition of reverse. Yeah. Okay, so we're not using reverse because it's a built-in. So we'll call it rev. It's version 1 of our reverse code. All right, so let's play with our reverse code. Looks good. So I try reverse of ABC, and yes, I get y equals CBA. Beautiful. And what list, if I reverse would give me CBA, and I get x equals ABC. Looking great. Everything works perfectly. And then I asked for another solution. So here, notice I didn't even get an answer. It just said, there's only one solution, this is it. Yeah? And you can see why, because the list always, right, has to choose which of these two rules to go, and said it's either an empty list or a non-empty list. There's only one choice. So it just goes to the right choice, the right choice, the right choice, and then finishes. Okay. Here, it gives me the right answer, and then I ask for another answer, and it goes off for forever. So what on earth is going on? Right? Now I have to hit Control C, abort, to get out, get back, because the computation's gone off forever. Okay. So we can look inside what's going on in Prolog, because actually it's a very simple computational semantics. And what this is called the bird model for understanding what happens. But there's some interesting things which are different. So normally when I look at a debugger, right, for a procedural language, I can enter a call and then I can exit the call, right? That's the two things that I can do when I'm debugging. I can sort of say, oh, I've entered this procedure, and now just as I return, I've returned from this procedure, and maybe I can look at the result. So that's normally what I do in a debugger. So in Prolog, there's a couple of other things that go on. So I can enter into our thing, and that shows me the call, so that's fine. I can exit if I succeed and I've got an answer. That's fine also. That's the normal sort of things I'm used to. But then what can happen in Prolog is, okay, something after me says the answer you gave me doesn't work for me. You have to give me a different answer, right? Because remember, every Prolog call can give multiple answers. We've already seen that. So it can ask you, come back and resolve what you're doing. Get the next answer for your particular question, right? So that's a redo call, backtracking into this to get the next answer from you, this little part of the code. And then finally, when you get no more answers, you fail. You say, okay, I've run out of answers, I can't get an answer, I fail, and of course then I'm going to call the person before me saying, hey, redo what you're doing, and then you can give me a new answer and we can try again. Okay? So, actually I think it's probably worth, okay, here, so this will show you what's going on in our call for reverse AB, right? Okay, so I start off with here's my call, right? It was reverse AB, and what's the answer, okay? Well, Y has been changed to this. So I'm asking the question, reverse AB, Y. So if you look at what happens for the code for reverse, right? It matches off this, and then it calls reverse with the tail of that list. Okay, so it calls reverse of B to get a new answer, and then it calls reverse of empty list to give an answer, which ends up being the same, right? Okay, so that succeeds. So these are 3 calls, and then there's a succeed. So reverse of empty list succeeds. Okay, so next, remember what happens after I succeed, right? The second last call for reverse, the last one was here and it succeeded, so now I'm back to here. So that's the next call that happens, right, in this recursive thing. Then I call append on the empty list, right, which was the answer I got from here. B, which was this, the head of this list, to get this result. And that succeeds, obviously, giving the result list of B. Right? And now basically I've finished this call. This call, how do you reverse the singleton list B? Well, you get the list B. Yeah? And then the next thing that happened, which is to do with this call, right, was I have to append that list, which I just got, with the A, that's the head of this list, to get the answer here. And then append says, okay, well, gives you this answer BA, right? And then I've now succeeded for the entire call. Yep. And then I answer Y equals BA. So that's exactly what happened in my reverse. Now here, I didn't fail, right? So I didn't push back into these things. I just succeeded. Every call succeeded with an answer. That's perfect, and that's very quick. And in fact, if you think about what happened here, every call, look at every call, we have the first argument is known, right? So we know which of the 2 clauses for reverse and which of the 2 clauses for append to use at every point. So there's no choice. So here we knew that this was a non-empty list, non-empty list, empty list. This was empty list, non-empty list, and non-empty list inside it, right? So in fact, this is not a creep, because, well, we didn't look inside append there. Right? Okay, so that's how it works forward. Let's run it backwards. Yeah? And we'll just do it for a singleton list. So I say, what is a list which, when you reverse, gives me A? Okay, so we don't know which rule to take, right? Well, in this case, we try to take the first rule, yeah? But that says that tries to match this thing with that head, yeah, and it fails. The second argument is a non-empty list, and the first rule has two empty lists, right? So that can't be used. So we have to use the second rule. Yeah. So we use the second rule, and now we've got, well, we know CBA, that's list A. We know nothing about these, so they're just unknown. So we just call reverse with two unknown arguments. Okay, so that's the reverse with two unknown arguments. And that succeeds, right, with the first rule. Right? In this case, if I take two unknown arguments, I can get empty list back. And then that result there is appended onto the unknown head of the first list, this list here, which gives me the list A. And so that succeeds, obviously. So the list A was this argument here. That succeeds, forcing this unknown head to be A. And so I've proved that the reverse of A is A. And I've got my answer. Right? So remember, the first answer worked fine. But now I ask for another answer. And notice, like this call here, I could have used both rules for reverse. And I've only used the first one so far. Right? So there could be more answers. Yeah, for this append call, there was only one possibility because it's only one thing. So, but there's a choice that I had at this call, which I haven't done anything about. Okay, so what happens when they ask for new answers? Well, it says, hey, redo that call, right? That call was the one where I had another choice. There's another way of proving this, so let's try that call. So I redo that call, I come back to the top, and in fact, this is a second call, a different call. See, the variables have changed. This is the call where I've used, I've had two unknown things here, and I call this with two unknown things, right? And that's got to be a warning, right? Call this with two unknown things. Okay. And of course that succeeds with empty list. And then I append empty list to the unknown head of this list here to get this. And that says, okay, well, that's the only way that can happen, right, is this. And I said, okay, I've proved that if I reverse this thing, I get this thing. Right, which is just a generic thing saying if I reverse any list of length 1, I get the same list. Now I've now got back to this call, the first call to reverse, and this is what I have to do. I have to take the answer I got from reverse, which is this one, right? I've got to append a new thing on the front, which is an unknown thing, and I've got to get A. Now this won't work. Okay. Right? This says I append two unknown lists of length 1 to get a list of length 1. No solution. Yeah. So it says, oh, well, that's no good. So was there something else? Well, yes. When I made this call here, I tried the first rule to get this success, but I could have tried the second rule. So let's go back and redo that call. Yeah? And so I do exactly the same thing, and I end up down here having that reversing a list of length 2 gets this list, right? So you notice this is generic reverse. This is any list. I've taken some number 663, 666, and I get 666, 663. I've actually generically reversed an arbitrary list, but then I have to append this list of length 2 to a list of length 1 to get a list of length 1, and it's going to fail. And then I'm going to find, oh, but there's this call to reverse here, and I've only tried the first solution here, so I've got to try the second solution, right? So actually what it's doing is iterating through all the possible lengths of lists that I could reverse, right, and finding that none of them will actually, if I append them to a singleton, will give me A. That can only happen for an empty list. Yeah? And so off we go to infinity. All right, but I hope you're now beginning to see exactly how Prolog is working. Basically, similar to our replacement. When we have a call here, right, we find a matching rule, and we replace that call by that rule. Yeah? I could even go... I think about it not in the debugger, but I say reverse 1 of, let's call it YAB, right? The first rule won't match, so I have to use the second rule, And the second rule says, okay, you replace that with reverse one of the head of this, right? So that's called BC to get CB. And then I get an append of the result of that, CB, with the head of this list, which I don't know. Let's call it A, to get AB. Right, but this is in the case that Y was split into two things, A and BC. Right, because if I think about, if I match, oh, I'm looking at the wrong one. If I match this thing here with this rule here, then the first argument, Y, was forced to be equal to A followed by BC. Yeah. So now I've got to prove these two things. Then I look at the first one here, then I said, well, let's try the first rule. So if I match the first rule, that basically says BC equals the empty list and CB equals the empty list. And then I have to prove this append. But now, since I know the CB, I get this. Okay, so I'm doing a slightly different example. Right? And this append will fail. I can't append the empty list onto a list containing a single element to get the list with two elements. So that's going to ask me, hang on, there's another thing you could do with this reverse. You could do the second rule. So we'll do the second rule. We'll replace that with reverse one of, let's call it BC prime, CB prime. And then the second part of that rule, which was CB prime, A prime, and the result, right, has to be CB. But when we did this, we also forced BC was equal to this A prime followed by this BC prime. It's getting a bit messy. Now, I do the replacement here with the first rule, or I get BC prime is empty, CB prime is empty, and then, so I got two append goals. The first one is now append CB prime, which is empty, to this A prime to get CB, and then I've got append of CB, this is the rule from up here, with A to get AB. Yep. So this will succeed, right? Setting CB equal to the list containing A prime. Yep. And then we can do this append call. We put the A prime there. And if that will also succeed, setting A prime is equal to A and A is equal to B, right? This is the only way I can have two singleton lists to append to get AB. And then I've got to look back at my answer for Y, which is what I'm trying to produce, remember? So Y was equal to A, so that's the list containing B, followed by BC. BC, so that failed, right? That didn't work. BC is here, is A prime, followed by BC prime. So that is A, followed by BC prime, and BC prime is empty. So that's that, which is in fact BA. Yeah? So Haskell, Prolog, is also basically a pattern replace kind of idea of computation, right? But here we're doing a more subtle version of pattern. It's not really pattern matching, because here we go, all right, if I see a call to reverse, then either I have to use this, right? And if that doesn't work, or I use this, either of them. I could use both of them, possibly. Right? So whenever I see a call to reverse, I either replace it using this, which basically says, oh, just make them both empty, and if you can do that, you're finished. Or you can do this. You can replace a call which is non-empty in the first part, otherwise it won't work, with this goal. Right? And so you just build up a bigger and bigger goal, and in Prolog we always take the first element of the goal to work on, and there's other things that's going on. You saw them here, right? We do substitutions happen. So here we substituted Y for A, B, C. Later on we substitute BC prime for empty list and CB prime for empty list. But we have also this other possibility that we could be going down some computation path trying to prove things and find, no, I can't prove this, So it goes back and says to the thing before it, okay, is there some other way you prove what you want to do to give me something else to work with, right? So that's exactly what this redo, right? So something later in the call stack says fail, so that tells all the things before it, okay, can you redo can you redo? Is there another way you can prove that that your bit holds? And if that's the case, then you'll end up calling me back again, right? And if you end up running out of ways to redo, then you'll have a fail, and then you'll call the person before you, right? Yep.
What can you force the length of the first argument to stop it from infinitely building up?
Yep. So for example, we could add, well, no, the problem is, yes, we could have here, if we added length of this is n and length of this is n, yep, then as long as one of them was known, that n would be fixed, right? So that would then force this to not go wrong, right? Actually, it's even a good thing to try.
So it would fail? Or?
No, it'll fail. It'll successfully. So basically, here there was nothing wrong with our code, right? It's just that it ran forever, right? So it didn't give back any wrong answers. But of course, running forever is not particularly beautiful, not particularly helpful.
But will it keep trying to build up lists before it can check them?
Well, not if we put the length first, right? Okay, so if we show the example, right? We had length of YA, there's the simple example we ran, and, oh, that's rev2. Got to run rev1. Okay, there it goes, off to infinity. Okay, so let's, unfortunately it's not so, can't jump to the editor directly. Let's have a look at reverse.pl, and let's add something in. Let's say the length of CBA is n, and we'll also know that the length of the other list, A, B, C, is also n. Yep. So let's constrain them to be the same length. And we do that before we make the recursive call, right? So if one of them has a fixed length, one of them will have a fixed length. And that should be enough. All right, so now if I try rev1 of YA, actually, it says it even knows that there's no more answers. Yeah, because I've basically forced the second argument. Instead of being anything, it's now actually a list of the right length.
So it's already explored all possible.
Yes. Yeah, so that's the difference. This the thing of the semicolon or not, right? Here, Prolog already knows there's only one answer. There's no more to look for, right? And it wasn't to do with it being length 1, it's to do with it, right? Oop, except I've got to type it correctly. Okay, here, all right, so it was to do with it being length 1. Ah! So what's happened? So here, yep, so we've run out of thing, because in the first call, we knew the length. So we've got to think harder, right? So in the first call, this had a fixed length, right? That had a fixed length of 3. But then this call, so ABC is known, it's like a length 2 thing. So, but something's going on. But CB doesn't have a fixed length. Okay. So now the problem is in the second call, CB is unknown length. Right? Nothing's talked about CB. And then I come in here and ask for the length of CB. So now it's going to try 0, 1, 2, 3, 4, 5. So I actually just move the error to somewhere, move the problem to some other part. Okay, but we'll fix it. Let me get back to the slides. Okay, so what we saw, right? So this is basically the thing I got through. Reverse 1 resolves to give you this goal. BC followed by CB followed by append CB, some A and then A, right? And this first call here, can produce an infinite number of solutions. Because basically, if you think about it this way, I'm just saying, give me two things which are the reverse of each other, right? So obviously there's an infinite number of solutions. Empty, 1, length 2, length 3, length 4, length 5, length 6. Yep. And then we make this call to CBAA. And of course, this will never succeed unless CB has a length of 0, right? There's no way this call will succeed unless CB has a length of 0. And so basically, we end up infinitely backtracking into this thing, producing the multiple answers and then discarding them, discarding them, discarding them. Yeah? All right. So this is where our infinite backtracking loop comes from. All right, so we could fix the problem for reverse by reversing the order. Okay? So if I do this, right? CBA, that's a fixed list, so append, that's a fixed list, so there's only a finite number of answers for this, and all of them have a fixed length of CB, and so always the second argument has a fixed length. Right, so if we do this, we'll get the right answer, and then we'll get false. But, unfortunately now, if we try the other way, right, we've just moved the problem to the other order. Right, so now if we give it an unfixed list second, and we come in with this is unfixed, so this is unfixed, so append has an infinite number of ways of saying, oh, I can append these lists to get an arbitrary length list, and then reverse has to check them, right? And the first one is okay, but after that it keeps just generating more, none of which will work. Yeah? So that doesn't look so good. All right, so this is what I should have done, what we were trying to do, right? Let's enforce that the two lists have the same length. But here we'll do it this way rather than using length. Okay? What is a constraint to force the two lists have the same length? Well, two empty lists have the same length, that's clear. And two lists, something followed by x's and something followed by y's, have the same length if x's and y's have the same length. Okay? So it's exactly what I wanted to write with length, right? Length n should work. The problem is that if I think about how length n works, it has an infinite number of choices in the front and then a single choice in the back. Actually, so it seems like it should work. But the second call, yeah. Now I'm confused as to why it doesn't work. All right, so this one will work in both ways. Exactly the same kind of thing as we're trying to do, but we do it from outside. It's actually a good question. Let's try that. It's just something because I put it inside the recursive call that calls the extra things. Let's do reverse 4. Should work as far as I can tell. I can't think of why. Right? So I'm doing almost the same as what I'm doing for reverse 3 there. So that works. No choices left. That's the easy one. What about the other one? Okay. Actually, I'm a bit suspicious that this solution doesn't work. So let's look at reverse 3. Okay, this is the interesting one. Oh, I've loaded it, yeah? Okay, so it does work. So it's to do with the interaction because same length, let's go back to the slides, now that I think about it, same length will be deterministic. If one of the lists is fixed, it'll only have one answer, right? So I'll get no choices left. If one of the lists that I give it is fixed length list, then this can't make anything wrong. right? Because it either uses this rule or this rule. So no choices. But when I do length n, even though it logically means the same thing, what it actually does is if the first one isn't have effects list, it'll just guess a length, right? And then give me n. Yeah, so I'm ending up with exactly the same problem. Right? I end up with infinite number of choice points on the length. None of them will work, but I don't know that until later on. So that's the problem.
When it guesses an n, alright, so it guesses an n, and then that n might fail, and then it
Yes.
goes,
And gets the next one. And it's the same problem that once I guess an n which is too long, and then I fail, and then I guess the next length n which is too long, right? So I basically, well, it's good to see that, you know, you can be confused about these things, even I, right? And so the difference here is same length will never make a mistake. It never has any options because whichever argument, right, is fixed, it will only have one way of answering. Always give a single answer back, right? Because it always knows if one of the lengths is fixed length, then there's only one way to go, no choices. So this is about basically illustrating that we don't want to put in choices, right, where we can't. So even though logically speaking, same length and length n is the same thing, not in practice. All right, so I've just gone way past an hour and a half, so let's have a break for 10 minutes. So be back here at, whatever it is, 7:52.
Several questions.
Yep.
First, can you give me an example of the integer word?
So that's rounding. Right? Float, I think coercion. So just that's right, from 4 to 4.0.
So it's just turn one type to another type.
Yeah, and integer of course is a rounding.
Yeah.
There's ceiling as well.
What
Yep.
are the backslash?
Okay, all right. That's a good point, and I should probably mention that. When in prologue we talk about this is the name of the predicate and this is the number of arguments.
Alright, so
So-
this one also tells.
Yes, it's just reverse 1 has 2 arguments. Yep.
So can I look at the RUV4 again?
Oh, AUV4, yep.
Yeah.
Right? So the problem is this will work as long as the first argument is fixed, because this will only have one solution, then this will only have one solution. But if the second argument is fixed, this will have an infinite number of solutions, and they'll be checked against this one. And so what I did was move the problem just to here.
So it means it will try the first one from 0 to infinite.
Exactly. I've set an infinite number of choices here, which will all fail, but of course they will all fail in an infinite amount of time. Yeah?
This reverse function is only applicable for 2 elements, right? And it's having a size of 2 elements.
No. Reverse works for arbitrary. I was just using very small examples. Because it's recursive, right? So reverse, particularly we go to reverse 3, which works well. A, B, C, no. If we've got to type it correctly. Okay, so there you can see at some point it doesn't print out everything. You can force it to, but I've gone a bit long. But I can go the other direction. Yeah? It's because it's recursive, so there's just 2 cases, empty or more than 1.
And how do you run that Haskell test file?
Sorry?
How do you execute that Haskell test file?
So, yeah, I think it's a bit tricky in Windows. So what you should do what I'm expecting you to do is something like GHC minus O2 minus minus make Haskell test. Right, whoops. And, okay, it won't work here, but that'll create a thing called Haskell test, an executable. And then I can use it, you know, black, queen, white king.
So what's the difference between Haskell test and project 2 test file?
Sorry?
Difference between Haskell test file and the project 2 test file? And both are different, right?
Oh, sorry, no, it's project 2 test that you want. Project 2 test uses Haskell test. So
Okay.
you just don't have to worry about it. It's only, right, so yeah, this is project 2 test that you want to do this.
Yeah, so that's all.
Yep. Yep.
I like your shirt, by the way. I also like your ring.
I should be putting it up for it's true, yeah, same things. But
Definitely Valve should be paying you for
Exactly.
advertising, right?
yeah, but I should have been wearing this for Haskell, of course, because Lambda is
Of course.
functional language.
What am I saying? May I ask just something about the assignment very quickly?
Yeah, sure.
Sorry, I know I should probably ask on the discussion board, but it's just racking my brain a little bit.
Yeah.
So what I've set up unfortunately, it's a little bit procedural in the way I've set it up, but my program does a lot of guesses because what it does is it takes the feedback and it just computes the next best correct thing. So we've
Yeah,
got,
okay.
So we've got
So you
zero-
just do the first one, which is
yeah, and then I just make it correct by doing some logic, and then 2, and then until it has all the right corrects, and then it has the right guess, right? Now that has a lot of guesses
Yeah.
in it. It does a lot of guesses. It's not generating every single one. It's
Yeah,
still
yeah.
doing it in a logical way. But unfortunately, it does have a lot of guesses. So I read your hints,
Yeah.
and I thought, well, that makes sense. You were basically saying, from what I understand, we could get our first initial guess, and then generate other possible targets as such, and then only check those targets.
well.
Right?
The simplest thing
Yeah.
is if you have a list of all the possible remaining guesses that are consistent with what information you already have, right?
Yeah.
Which I think that you've got. Yeah.
Yep, yep.
So you're sort of removing. Well, so the thing is, in Haskell, it's just as easy to just think about filtering out any guess which is no longer valid.
Right.
Right? If you've got that list, then you can think, if I made this as my guess, then what answers would I get from all the other ones? Right? That's what the third hint is about. If I made this as a guess, what answer would I get from all the other ones? And if those answers are really all different, that gives me lots of information. And then you look at the second one. If I made this as my guess, what information will I get from all of the possible answers that could be? If those are really, really similar, then I get less information. And so basically you're trying to pick the guess which would most narrow down the possibilities. Right?
So similar to doing this, but
Yeah,
making
it's
it
similar
so-
to doing that, but you're just going, well, I'm just going to get the first guess that would work and go, right? And then there's more. I mean, particularly at the first guess you have nothing, so if you can do this in the generic case to go, what's the best first guess for the, right? Because some guesses will be really, really bad. So imagine, I mean, if I said my first guess was black pawn, black pawn, black pawn, black pawn, black pawn, right? I don't learn very much information, right? Because I basically learn how many pawns you have and how many blacks you have, but nothing else, right? So that's probably not the best first guess to make, right? So you've got to think also about what the first guess is, because that starts you on the chain and gives you good information. But I mean, at least for my solution, yeah, I mean, the first version of the program I did was exactly the same. Just get the first legitimate guess and ask that, right? And that's not too bad, unless the order you've got them is really bad. So think about that. Maybe your order is wrong because pawns are not very interesting.
Yeah. So it's extremely efficient, but in terms of guess complexity, it's very high.
Yeah.
I've written, so.
Yeah, so you need to work on that because you're going to get marked on guess complexity, and you've just got to use your 10 seconds.
Right,
Yeah.
No worries. Okay, thank you for that.
Okay.
I have a question about SWI. I want to
Yep.
change it so the background is black and the text is white
Oh,
because it's
God.
blinding me.
Okay. I have no idea about that. But that
'Cause it doesn't need to
shouldn't be to do with SWI. But it's in Windows, is it?
Yeah, it's in Windows.
So it's popping up its own window. But it should
Yeah.
be that it's using someone else's window.
I managed to get it Like I've tried to change some settings, so I've managed to get all the like text symbols like, internal to it to change the color, just not the default.
So, yeah, and the problem is I don't know what it's using to pop up its terminal window, but it will be a known terminal, and if you can find that, and there should be some options somewhere in the SWI prologue for Windows documentation. So I would search now, how does it pop up this window? So it's because it's going to use some shell emulator from something. And so it then should have a way of sending some options to that shell emulator to do it. But that's my best guess.
Yep.
Okay. Yeah, the problem is if Unix, it's just its own. So with the window, you just have to fix the window and then it doesn't do anything. Right. See, you should just never use Windows. That's the key. No, there are no good reasons to use Windows.
There are no good reasons.
Yes. Yes, there are reasons, I agree. All right. So, hopefully you've seen how, as I come back and load my prologue knowledge back into my brain, moments too late to not get trapped by a very good question. Right? When we're writing prologue code, we basically have to make sure that when the way we use it, we don't end up generating an infinite number of solutions somewhere, right? And then checking them afterwards. Because if that happens, we'll never be able to prove that there's no more solutions. Because if we've got any call which generates an infinite number of solutions, then it's fine. The rest of the things will check them and say it doesn't work, but we'll always keep going back and get another solution, then get another solution, and get another solution. And that's why the same length works, because regardless of which two of these arguments are fixed, it'll only give you one solution. And so by the time we get here, both of these things will be fixed length, and then everything will work fine, right? Whereas the length n version, which looks to be the same, doesn't work because one of those calls, if the first call, so in this case, I put length of ABC as n and length of CBA as n, if the first call has unknown variable ABC, then it can generate an infinite number of lengths. And so I'll never be able to prove there's no more solutions, because that call will always say, oh, I can find you another length for ABC. It could be 5, could be 6, could be 7, right? Even if immediately after that, the call to CBA will say, hang on, I know CBA is length 3, so that can't work, right? But I'll still generate those infinite number of lengths for the first argument. Yep. Okay. So, append and length both work in all possible modes, right? So they generate a finite number of solutions as long as either the first or the second argument is ground. Oh, first or last, sorry, because length has 2, but append it's the first argument or the last argument is ground. Otherwise they generate an infinite number of solutions, right? So if we look at this, I want you to tell me which modes will these work, right? These two different versions of tape, where it's just all I've done is reverse the order of the body. Will they always work without hanging? Will we never get a case where we can generate an infinite number of solutions? Right, so I want you to work out how I could use these two versions of tape without getting any problems. Right? And when I talk about a mode, I mean, okay, remember, a mode is just, okay, in, out, in, for example. All right, I'm giving you a fixed argument for n and front, and I want the list as output. Or out, in, out. All right, the opposite. I'm going to give you the list as input, and I want the length n and the front as output. So I want you to look at these two different versions and think about which of those will run without hanging. Right, so we know as long as we, for append and length, as long as we give them a fixed first or last argument, they'll only give me back a finite number of solutions. So please write it down, commit. Type it in. Right? So if you think about it, there's 8 possible modes. There should be some which are fairly obvious will hang. All right, I see people waiting. Okay. All modes, but out, in, out. This is going to work. Okay, in the assumption, so out, obviously can generate an infinite number of solutions, but actually will generate them, right? It can't get stuck into this thing. But if you think about what we call without, in, out, right? So this is known, neither of these are known. So then this thing can generate an infinite number of answers, right? Because I don't know either of those, so I can generate an infinite number, and then some of them, so then I can append. So for the small ones, let's say this list has length 5, then as long as these answers are less than length 5, this append will succeed, right? Because there is the first 0 characters front list, this first one element of this list, the first 2, first 3, first 4, first 5. But then when we try 6, right, I try to append a length of, I take a length of list 6 and something and get a length of list 5. Never going to happen. And then I go back and try 7 and 8 and 9, and they keep on failing, right? So out actually doesn't hang because it'll give you an answer, right? There's always another answer. So that's the only thing will go wrong. In the other cases, as long as one of these is in, if this is in, right, then length, this is in, and so there's only a finite number, there's only one answer to length. Once there's only one answer to length, then front is a fixed length, and then there's only one answer to append. Yep? If this is in, if front was in, then that's a fixed length list, so this has only one solution with n fixed, and then this is fixed, so append, remember, once I have a first argument fixed, has only one solution. All right, no problem. Okay, so here it changes. Here it works in all modes, but out in the last two. Right? Because if we think what happens here, n is fixed, but this call, nothing is fixed. Right? So there's an infinite number of ways of satisfying that append rule. Yeah, and some of them will be fine. We'll start with like empty list. Right? Yep.
So what will happen with
In, out, in here or here?
the right
Here? Okay. I'll just show you what happens with in, out first, then I'll do in, out, in. Okay? So this can give an infinite number of answers. And the problem is once they get big, so then we check whether this list is the right length. Right? So let's imagine that n was 3. So this will give me an answer, you know, empty, and then 1, 1, 0, 1, etc., and then I'll get an answer of front is 4. And then I'll get, okay, the length of that is not 3, and so it'll fail. Then I'll come back here, and I'll try some other lengths, but I'll get a length of length 5, and this will fail. And then I'll have my infinite execution. Let's try in, out, in, the question. Okay, now in, out, in, so front is fixed. Yep? So as soon as front is fixed length, then there's only one solution to this. Right? And then I check this, and they're both in, so that's easy. Only one that can only fail or succeed, right? Oh, sorry. Yeah, there's only one solution for append. Okay, now let's look at append code, because that's a bit subtle. There's append. Oh, there. Okay, the first argument is fixed. Yep. What happens to append? Maybe I'll do it here. I do append of, let's call it A, B. So I don't know what the elements are, right? L, R. Then I match on the second rule, can't match the first rule. So that says I should call append of B, the list B, for L and R prime. And actually this R prime here, R is equal to A followed by R prime, right? Because I have to match R with A, B, C. Yep. So then I get this call, and that only matches the second rule, and it says I have to do that, and here R prime is equal to B followed by R double prime. Yep. And then I get to this call to append, and this just says, okay, those two things are the same. All right, so that finished, and I said, well, R double prime equals L. And so I finished, and what did I give my answer? I get this, which is exactly the result of appending AB on the front of the list L. Now, it doesn't matter what L is, right? Append never really looks at the second argument. All it does is carry it along, right? We saw it got carried along, and then it got stuck in the data structure at the end. Because it's already a list, I don't need to do anything. Yeah. So that's why append, even if there is an infinite number of solutions, because we don't know what L is, it doesn't not an infinite amount of computation because they're all encapsulated, right? This append call shows you all possible answers for a list of length 2 appended to anything. No other answer you can get. You can only get this, right? Doesn't matter what an AB are, doesn't matter what L is, these are the only possible answers you can get. Yep. Okay, so that's why in, out, in will work. As soon as I have front as in, basically I'll get one computation out of this, right? There's only one answer, even though it encodes an infinite number of possible answers. There's only one computational answer, because as soon as I know the length of this list, I've got no choice about which clause for append to use. I can't use the first one or I can't use the second one, so there's only one answer. Yep. Right, it's more subtle, but like out, out, out obviously gives you an infinite number of solutions, but it actually will just keep on generating solutions. It will never get stuck looking for another one because there's always an answer because you haven't fixed anything, right? The things where it go wrong where you fix something, right here you fixed n, but you check it at the end. Here you fixed list, but you only check it at the end. Yeah? You only make use of it to check at the end. And that's where you can get this infinite generation and then check. And infinite generation followed by check ends up being hanging. Yeah? All right, so I guess we can, let's have a look. I should probably do some more of this. So I can run the debugger. So I turn on trace, right? I can actually see all of these things in operation. So let's do the simple case. Oh. Right. So there's the call, and I hit return, then I creep to the next call, right? And then I got the answer to the first rev. This is what we saw on one of the slides, basically. Yep. Then I failed because that append didn't work, right? If I took the empty list, reversed it, wouldn't work. So I come back, I try the next answer. Okay, then I get a list of length 0, which if I append to the first element, I get a list of length 1. That gives me this. Okay, I proved that inverting an arbitrary list of length 1, you get the same list. And now Oh, sorry, I've just hit the wrong button. Show context. Oh God. Now I've got into all kinds of things. Okay, now we're back on track. Now I have this call to append, which obviously works, right? I can split this length of list 2 into 2 lists of length 1, doing that. And that's the last step I needed to do before proving reverse. Right, but then without semicolon, we get into this redo. So this is where we want. Now, one thing I can do is I can say, okay, if I get to a call, I can just skip. Right, I can skip, okay, that's what happens in append. Well, actually, that already worked. I can try skipping this reverse. Creep. Okay, I can do help. Yep. I can set a spy point. So if I set a spy point with plus, if I can't type it correctly. So now I can go leap. So I'll leap to the next thing about reverse 1. Right? So I'll see only the calls to reverse 1. Right, exit, exit, exit. And actually, I should have a redo in there, yeah. Okay, so reverse 1 is not where the redos are. Why am I not seeing redos there? Okay. Let's try something simpler. Okay, so most often when you're using the debugger, you'll set a spy point on the thing you're interested in and just, okay, then we see exactly what happened in the reverse recycling calls because we know how append works, so we don't care about it. Right, so leap, just skipping over all the appends, and I'm done. All right. So I can obviously abort, right? A break, I can actually set up a thing, I can do a listing, right? So I can look at my code, right? There's the code for reverse 1. Whoa. That is applicable at this thing, right? That's the rule that I'm going to use for reverse 1 on this call. I can also like force a retry, so oops, I need to get to an exit port. So retry this, okay? So I can that's quite useful when I'm debugging. Actually, I'll get out and talk about the. So basically, but the main ones are creep, which is just move to the next call to see what's going on. Skip, which is okay, if this is a call, I'm going to either get to the exit or to the fail, because that's the only thing that can happen in this call. So I'm going to not look at what's happening inside, and set up a spy point and just leap to the next spy point. Although why I wasn't seeing redo events in the spy point, I'm not sure. Okay. Yes, so back to the initial call port. So that's useful if you see something going wrong, but you leapt over it. Right? So imagine you skipped over an entire thing and it'll give you back an answer false. Then you want to do is redo. So now you redo the thing and now you creep. So you creep inside to see where it actually went wrong inside. Right? So I said plus set a spy point, minus set a spy point, leap to the spy point. You can also pause the debugging thing and enter a whole new Prolog shell, make a new query. So you might go, hang on, I don't expect that answer. You might go, oh, if this, it should have run the same as this goal, and you can run that goal and see what that goal does, and then come back out, right? But that's a bit more complex. Okay, so other thing you can do in your code is you can say, put a spy on a predicate, right? So that just puts a spy point on that predicate. Now, one thing that I haven't pointed out, it's been implicit in these codes, is that in Prolog, let's find it there, we tend to write names of predicates and functions like this, right? So this is reverse 1, that's the name of the predicate, and it takes 2 arguments, right? So name of the predicate / arity. It's because in Prolog we can have another predicate called reverse 1 with 3 arguments, which is a totally different thing, right? This is the kind of opposite of Haskell, right? In Haskell we have currying, every function actually has one argument, even if it actually needs 3 to evaluate, right? In Haskell, every function has one argument. In Prolog, every procedure can have any number of different arguments, but they're all different procedures. Yeah. So you can ask to spy, so you can just have the predicate name, in which case it'll actually put a spy pointer on all predicates with that name, or you can have predicate name arity, which means only on the one with that particular arity. Yeah? And we can say no spy, traces to turn on the debugger. Debugger will turn on the debugger and leap to the first spy point, but that's if you're in the middle of computation, and no debugger turns off the debugger. Right. And so, yes, this predicate specification can either be name, basically means any predicate with that name, or name/arity, which means exactly the predicate which has this many arguments. Yeah. All right, and well, this is what I was talking about. This retry is very useful, but I think it's probably best we'll come back, we're already running late, and I'll come back and actually show an example of debugging some code using this approach. We'll get back to that next time. All right, good luck with the assignment. It is due this Thursday, as you must be well aware already. And you should be glad that I didn't make horrendous late penalties as I said I would. After looking at how easily you could be late in the first project, but I didn't change the rules, so the lateness just fine in the project still works. Yeah.
Sorry. The project specifications have at least 10 seconds to guess each time. It means that, for example, this is a one target.
That whole thing is one target.
Whole thing is one target.
Yeah.
So it means that I must finish my guess to get. I must complete my guess in 10 seconds.
You must complete the whole finding the correct answer in 10 seconds.
Okay.
Right, so that can be quite tricky for a size 32 game.
Yes. So,
right?
so
and there's this trade-off between, because sometimes you can be quick,
yes,
but stupid,
yeah.
and you can be smart and slow. And at least in my solution, I only start being smart when there's not too many solutions left.
Okay. Another question is if I test for about 10 times, it means I have 100 seconds.
Yes.
I understand. Thank you.
Yeah.
Just wondering how I can figure out if it's my guess. I mean, my program is running more than 10 seconds, but it's not.
So if you're on Unix or Mac, you can go time and then run it, and that'll tell you the time. Okay, I mean I can show you. If it's Windows, you're in a more difficult environment. I don't know. There must be some tools in Windows to check the amount of time. But also, I mean, even walk-up time. I mean, if you aim for 5 seconds, you should be able to judge, right? So, for example, here I can go in Windows, in Unix or Mac, I can just go time and whatever process. I've got to think what I want to do. Cat. Right, and there. At the end, it just tells me the time. Right? So if you've got Windows or Mac or Unix, you can just put time and then, so you'd be going time, project 2 test.
So if I run that on the universe service, I should be able to use
Yeah, exactly. So project 2 test, 5, whatever, BW, and you'll be able to see it. Yep.
You're saying that putting pawns, like, because the way I started, like, I always put black pawns all over the place, just try to avoid things like
Yeah, but you've got to think about how much information you get from pawns, right? So if you go 8 black pawns is the first thing, then you're going to learn how many pawns there are, right? And how many blacks there are, right? But you'll learn nothing else, right? But if I put lots of different things, I could learn, I might learn if none of them come up, for example, right? Then I learn there's none of any of these pieces, so I learn more. So in some sense, I mean, the proper way to do it, you can try it with small examples, you can't do it with a full 32, is you can actually just try. For every guess, how many possibility answers could I get? And you want the guess which sort of splits the space into as many different answers as possible. Right? I mean, basically, that splits them. You get the see. Because think about it. Every guess, from every guess, you get back an answer, right? And that allows you to wipe out all solutions except the ones that fit those answers. So if you make a guess, which almost all the possible answers would give you the same thing, and you get that back, you don't learn very much, right? So you want to make a guess which kind of breaks all of the groups of possible answers left into small sets, right? So that whatever one it actually is, you'll get very small, very many fewer things left in your answer. And if you do that, then it'll make a big difference, right? But so it's also arguing. I mean, for the first guess, you can try to do it from first principles, but I was just trying to example that, you know, okay, black pawns all seems like it might be strong because it might wipe out pawns, but then there will be plenty of solutions, plenty of guesses with no pawns. Yeah. So all you get is there were no pawns, right?
Just remove all the pawns from your set. It depends
Yeah. I mean, so yeah, that's true. If you definitely know exactly how many pawns you have. If you have 8, right? Because that's the maximum. Oh no, because you can have 16. Anyway, so if you had all 16 pawns there, you could count exactly how many things you had. But that actually doesn't wipe out that many guesses, because there are plenty of guesses with, you know, then you've got to look at the rest of the things. And there's lots of ways of having knights and rooks and blah, 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 right? So, I mean, it's counterintuitive because, okay, it gives you some strong information about pawns having all 16 pawns, but actually that may not differentiate a lot of guesses. Because if you think about, just take a random solution, let's say a size 16, right? Then I'm going to have probably on average 8 pawns, right? But that's not that. I mean, if I make a guess with no pawns in it, I also find out how many pawns I have, right? Right? Well, once I get the right guesses for the other ones. So it's even though it may look like it gives you a lot of information, it actually, what it doesn't do is it doesn't split up the other guesses very much, right? It splits up guesses depending on their number of pawns, but it doesn't tell you very much else. So you should try. I mean, at least for my thing, I tried it for all solutions up to 4 or 5, and I found the best possible one first guess, and then I just extrapolated from that.
But then, does it work equally well for a large size, like for 32?
Well, I don't know, but because I could imagine why it wouldn't.
Yeah.
But I think I'm pretty sure my answer for 32 is right. Because there's another thing you can think about, right? So, like if I have an aim of size 16, should I make a guess of size 1?
Yeah, but should we try to make it work really well for small sizes and not worry so much for...
So, yes, most of the testing is on small sizes, right?
Okay.
It's explicitly in there, right? I said, I think in the fora I've all said, I mean, you can get 85% of the marks even if you don't work at all on the big sizes, right? So because to work on the big sizes, you actually just have to be quick in some sense, right? You have to be quick to get it in, even though it actually turns out you can still be. I was amazed. I mean, you can. My thing never takes more than 7 guesses, I think, even on the big ones.
My one big one's thinking like 11. So.
Yeah, well, that's not bad, right? I mean, there's a lot of possibilities for all 32, right? So 11 is pretty good. And if you can do 11 in under 10 seconds, then, you know.
I think it is, but then for the small size, it's like 7.
Okay, so then you need to be working more on. So I think, you know, so if you've got some cleverness in there, this is the thing. I think I've put it in the forum as well. For a small size game, you can afford to spend more cleverness, right? Right. So that's where you can get it down to 5 or that kind of guesses. But even then, I mean, look, I don't know really where that median's going to be, because I see people in the forums or sending me email directly with, you know, guesses of length 24 or something like that, right? And I expect if you've done even hit 3, then you should be down more like the 7 or whatever, right? So, or less. So
yeah, sometimes I'm getting 4.
yeah, but you can be lucky, but it's really the average.
Yeah.
And so, but yeah, so yeah, I mean, don't concentrate so much on the big ones. It has to work for the big ones to get all the marks, right? But
You're not stringent with the time constraint of 10 seconds.
I am stringent with the time constraint, and if you don't get an answer in 10 seconds, you get 0. Okay, but remember, you've got the size, so you can do more work if it's a small size and less work if it's a big size. Right? So you can make use of that.
Okay.
So you don't have to do the same thing every time, right?
I just have one question.
Yep.
How many simple test cases are there? Because when I submit it, it just abruptly stops. Like for the first project, it showed me that these many out of 10 test cases.
Okay, so in this thing, you don't get to see the actual testing. The visible in your verified feedback, you'll get like 5 test cases.
25.
Yeah.
Okay.
Okay, and there's lots more test cases that are going on behind, but you don't get to see them. Okay, because this, I mean, for a small project, then I'm happy to, I mean, the problem is that then I'll get solutions which are just good enough to pass the tests, right? Which is not what you want. You want solutions which are really as good as can be and they pass the tests, right? So if I show you the testing, then it pushes you to do the wrong kind of programming. Yeah?
Okay.